Hello everyone, this is the lecture series of Operation Research subject and the course code of this subject is ME405 and present time unit number second is running here and lecture number is 16. This is the last lecture of unit number second and today I will discuss about the dynamic programming related to Operation Research and for my introduction, myself Rahul Kumar, Assistant Professor, Department of Mechanical Engineering, Suresh Gyan Vihar University, Jaipur. And for the introduction of dynamic programming basically provide the optimization related problem. Or it gives a optimal solution. It gives a optimal solution for both a mathematical optimization method and in computer programming method also, right? And it divided a main big problem or main complex problem into a sub problems, different types of sub problem. And this method developed by the Bellman at 1950, and it's this method is very useful for the aerospace application, economics and transportation related problem, and they find the uh, neural network and different types of computer programming and bioinformatics. This method is very useful in bioinformatics also. So this is very important and very easy method for the solution of different kind of dynamic programming problems. These are the objectives of dynamic programming problem, and dynamic in the short form of the dynamic programming is the DP, and it is used to solve a wide variety of discrete optimization problem such as scheduling, string editing, packaging and inventory management. Means it can manage the inventory management also, and the student able to understand about the break problems into the sub how to main problem break into the sub problems and combine their solutions into a solution to the larger problem, right? And it also provide the information related to contrast, to divide and conquer. There may be relationship across sub problems. Means if big problem divided into the sub problem, this is called the conquer, and how to produce the conquer in this dynamic programming problem. So we will go to the introduction part of this problem. As I said, dynamic programming is a general algorithms or design techniques for solving problem, and it also give the mathematical optimization method and the computer solution. And the method was developed by the one American mathematician, Richard Bellman, in 1950. They solved the different kinds of optimization problem related to the operation research and the bioinformatics and all other related things like as a neural network and sound technology also related to this optimization technique. And these optimization techniques are both exist in the problem, the main problem breaking into the sub problems, and the these sub problems like as a recursive manner. While some decision problem cannot taken apart this way, and These decisions that span several points time often break apart recursively, and the main idea about this problem related to the dynamic programming and other types of programming related to this. The main idea, it also set up a recurrence relating a solution to a larger instance to solutions of some smaller instance, and it solve a smaller instance once. It also record solution in a table, and the main idea about this problem is here it gives the exact solution to the initial instance from that table is here. So this is very good tool to optimize the mathematical problem in the terms of transportation are different types of related problem, and except from this, the dynamic programming is an algorithm technique which is usually based on the recurrent solution formulation and one starting states. A sub-solution of the problem is constructed from previously found ones, and the dynamic programming solution have a polynomial complexity which assures as a much faster running time than other techniques like backtracking and the transportation also. Now let's go through the one example related to dynamic programming. Then here this is the example, and this is a main problem divided into the sub problem. Here this is the combination of problem. This is the n minus 1k plus n minus 1 k minus 1, and this problem is divided into two parts, n1 equal to 1 and n equal to 1, and this is called concur of the main problem, and a divide or concur approach would be repeatedly solved the common subproblem, and dynamic programming solves every subproblem just once and store the answers in a table. Just once it stores the answer in a table. So this is a use of optimization in problem. Means what the use of optimization in this problem? A set of choice must be to get an optimal solution. First, for the case of transportation problem, first you find the initial basic feasible solution by the help of WAM method, Northward, NCWR method, and one more is least cost method, LCM method, and then find the optimal solution with the help of stepping stone method on the or any one method is Modi method. Then you do here find a solution with the optimal value, minimum or maximum. These optimal value which belong to minimum or maximum values, and there may be many solutions that lead to an optimal value, and then if you find the optimal solution, then the optimal solution and this solution in the case of minimum or maximum quantity. So the main goal of this analysis and solution is here find the optimal solution. Then go. These are the four types of dynamic programming algorithms. First, you characterize, recursively, compute, and construct. These are the four types of dynamic programming algorithms, and first is characterize. characterize the structure of the optimal solution. In this step, you characterize the you differentiate the solution structures by the optimal solution and recursively define the value of the optimal solution. You can define the value of the optimal solution also and compute the value of an optimal solution in a bottom up fashion and construct an optimal solution from computed information, not always necessary, and construct an optimal solution from computed information, not always necessary, right? So these are the 4 steps. This is very important for dynamic programming algorithms. And we move to the next step. And the next step for this algorithm is an algorithm design method that can be used when the solution to the problem may be viewed as a result of sequence of decision. And dynamic programming is a very powerful techniques or very powerful algorithm technique to solve a particular class of problem, and it demands very elegant formulation of the approach and simple thinking, and the coding part is very easy. The idea is very simple if you solve problem within a given input, right? And it uses 2 types of approaches. Means dynamic programming algorithm uses 2 types of approaches. First is top-down approach and second is bottom-up approach. For the top-down approach called the memoization, and the bottom-up approach called the dynamic programming. And for the top-down approach, start solving the given problem by a breakdown, right? Breaking it down, if you see that the problem is already solved, then just return to the saved answer. If has not been solved, and solve it and save the answer. And this is usually easy to think of very initiative, and this is referred as a memoization. And for the bottom up techniques, analyze the problem and see the order in which these subproblems are solved and start solving from the trivial subproblem up towards the given problem. In this process, it is guaranteed that the subproblem are solved before solving the problem, and this type of programming is referred to as a dynamic programming. Here, the divide and conquer is slightly different techniques, and this type of way to finding the result, this is a very good result for the optimal problem. And the dynamic programming algorithm stores results or solutions for small subproblems and look up them rather than recomputing them when it needs later to solve large subproblems, and typically applied to optimization problem. Means this is a very typical easy way to method to apply this type of problem. And in the recursion uses the top-down approach to solve this problem. That is, it begin with core problem, then break it into the subproblem and solve these subproblems similarly. In this approach, same subproblem can occur multiple times and consumes more time to solve the problem, hence increases the time complexity. And whereas the dynamic programming, same subproblem will not be solved multiple times, but the prior result will be used to optimize the solution. and the main objective of this problem is optimize the solution of the problem. Then come to the point. Here is principle of optimality, and principle of optimality the principle of optimal policy has the property that whether the initial state and initial decisions are the remaining decisions must be constitute an optimal policy, and this optimal policy with regard to the state resulting from the first decision, and this optimality policy or principle of optimality given by the Bellman at 1957. And an optimal sequence of the decision has to the property, right? Has to the property, and that whether the initial state and decision are the remaining decision must constitute an optimal decision sequence with regard to the state resulting from the first decision. Essentially, this principle states that the optimal solution for a larger subproblem and contains an optimal solution for a smaller subproblem. Means this type of problem refer to a larger subproblem and which also contain the solution of the smaller subproblem. And in the case of computer science, a problem is that can be broken apart like is said to be a optimal substructure. Means this big problem divided into a optimal substructure, and in the context of dynamic programming and the game theory, this principle is analogous to the concept of subgame perfect equilibrium, although what constitutes the optimal policy in this case is conditioned on the decision makers, and this type of decision maker policy is called the principle of optimality, right? And the dynamic programming method breaks the decision problem. The dynamic programming method breaks the decision problem into a smaller subproblem, and for this reason Bellman principle of optimality in this case is here. In this case, the initial problem divided into the subproblems also, right? And then move to the next slide. Suppose this is a one example. So consider the problem of finding a shortest path. Consider a problem finding the shortest path between a pair of vertices in a cyclic graph. An edge containing node I and the node j has cost Cij. So here, suppose source is I and j is the destination, and the cost associated to transfer the goods from source to destination is Cij, and the graph contains n nodes, and the graph contains n node numbered 0, 1, n minus 1, and has an edge from node I to node j only if I less than j. So node 0 is the source and node n minus 1 is the destination. 0 is the source and node n minus 1 is the destination. So let fx be the cost of the shortest path from node 0 to node x, right? In that case, the fx be the cost of the shortest path from node 0 to the node x. So for this case, the function is fx equal to 0 and this function is minimum if 0 less than j less than x, then the minimum function is fj plus cjx. Here x equal to 0, then fj plus cj only. In this case, 1 less than x and x less than equal n minus 1, right? And n is the number of nodes here. N is the number of nodes. This problem converted into the graph. Here 0 nodes breaks into the two smaller two constituent nodes is here 1 and 2, and this is the cost associated with the 0 and 1 destination. So the cost is c 0 comma 1. Here is cost is c 0 comma 2 is here, right? And then this one is divided into two parts. One branch is meets the second node and other branch meets the third node. And in the second node, this is the combination of 0 node and the 1 nodes. Here the cost is c1 comma 2 and the here cost is 3 1 comma 3, and this is the c2 comma 3 and the cost associated with 2 to 4 here c2 comma 4 and here 3 to 4 here c3 comma 4. A graph for which the shortest path between node 0 and the 4 is to be computed, then f4 equal to minimum f3 plus c3 comma 4 plus f2 plus c2 comma 4, right? So this is the f4 nodes for this analysis. So the solution of the dynamic programming is typically expressed as a minimum or maximum quantity, and this is a possible alternate solution. If R represents the cost of the solution, then the solution composed of the subproblems like as a x1, x2, xl, and R, this can be written as R is a function of g equal to function x1 comma function x2 function xl. Here g is the composition function. If the optimal solution to each problem is determined by composing optimal solution to the subproblem and selecting the minimum or maximum, the formulation is said to be dynamic programming formulation. Then the formulation is said to be a dynamic programming formulation. For this, we can give the different types of solution here for the dynamic programming, and we meet the different types of constraints here. So we move to the next slide. This is the dynamic programming example. So here this is square is the minimization of the term, and the circle shows the composition of solution into a term. Is here. So fx1, fx2, fx3, fx4, fx5, fx6 and fx7, these are the functions, and these functions related to the r1, r2 and r3, and these all associated with fx8. This is the minimum function of r1, r2, r3. So here in this case, if function x1 and x2 which means there the r1, and in this case fx2 fx6 and fx7, this is a r3 function, r3g fx2 comma fx6 and fx7, and for this case r2, here x4 and x5 meets a 1 point. This is the composition point. Circle shows the composition point, and these all variables meets at the point of fx8 function, which is a minimum function of R1, R2, R3 axis, right? So this is the graphic one way to solve a big problem into a smaller one, right? Here this is the dynamic programming recursive equations, is also called the functional equation or the optimization equation. Means the equation is formed by the at the last solution. This is called the optimization equation or the functional equation. And in the equation of the shortest path problem, composition function is fj plus cjx, and this contains a single recursive term fj only, and such a formulation is called a monadic. And in the right hand side it has a multiple recursive terms. The dynamic programming formulation called as a polyadic. So these are two types of terms are used here. One is monadic and the polyadic, and this and the monadic contains only single recursive term, and this is the best example for the previous example, which contain the single recursive term. This is, and that solution or problem referred to as a monadic. And if the right side is multiple term is used, then the DP formulation is called the polyadic, right? So these are two kinds of approaches used in dynamic programming analysis. In the above case, we conclude that the dependencies between the subproblem can be expressed as a graph. If the graph can be levelized, that the solution to the problem at a level depend only on the solution of the problem at the previous level, and this type of formulation is called the serial formulation, else it is called the non-serial. If this dependencies and solution, this it does not depend on the previous level, then this is called the non-serial solution. If it is depend on the previous level of problem, then it is called the serial solution, right? So based on the two criteria, means serial and non-serial solution, we can classify the dynamic programming formulation into four categories, and these four categories are serial monadic, serial polyadic, non-serial monadic, and non-serial polyadic. So this classification is useful since it indicates the concurrency and dependencies of the problem, and it also guide parallel formulations method, right? So here are the four formulation method. One is the serial monadic, serial polyadic, non-serial monadic, and non-serial polyadic. These are the four type of case, and which these four cases based on the criteria of two criteria. What are the two criteria? First is serial and second is non-serial. And serial criteria based on the if the sub problem relate to the previous level of the problem, then this is called the serial. If any sub problem which does not relate to the previous problem, then this is called the non-serial solution, right? So for this study, this is converted into the four types. These are given in this slide. So I am again repeating the name of these four types of serial monadic, second is serial polyadic, and third is non-serial monadic, and fourth is non-serial polyadic. Means only you learn only two things: serial monadic and serial polydic. And in two, these are serial and two non-serial, right? So these are the different quantities related to the dynamic programming. And first is here serial monadic dynamic programming formulation, and this is very difficult to drive canonical parallel formulation for the entire class of formulation. But in this case of this is represented by the two method. This is represented by the two method. One is the shortest path method and another one is 0 by 1 can aspect problem. 0 by 1 can aspect problem. And we drive parallel formulation for those problems and identify common principle guiding design within the class. So first we define the shortest path problem, then we go through the 0 by 1 can aspect problem, right? These are the special case of shortest path problem, and in this type of problem the graph is weighted multi-stage graph of r plus 1 levels. Here we are using r plus 1 levels, and each level assumed to have n levels, and every node at level I is connected to every node at the level of I plus 1 nodes. And if level 0 and R contain only 1 nodes. If level is 0, then the R contain only 1 node and the source and destination nodes respectively. And the objective of this problem is to find the shortest path from S to R. Means S is the source and R is the destination of this problem. So we find the solution of this problem for the next step. So here in this problem, this is the S is the source and R is the destination of this problem. So for solving this problem, here different types of V10, V11, V12, these are the different types of destinations, and this is a second destination V20, this is third V30, similarly VR10, and in this case VR1 and -1. And it can uses by, and then all types of routes and all types of costs associated with this programming, it will meet at a point R also. And this is a example of a serial monodynamic dynamic programming to find the formulation of the shortest path in a given graph whose node can be organized into level. So first you find the cost associated with it. If cost is less, so this is the shortest path of this problem. And then move to the next step of the problem, and these are the shortest path problem. In the shortest path problem, ith node at level L in the graph is labeled VIL, and the cost of this edge connecting VIL to node VJL plus 1 is labeled CIL, J. The cost of reaching the goal node R from any node VIL is represented by CIL also. So these C denote the cost of the transportation, right? And if there is n node at level L, the vector C0L, C1L, Cn minus 1L, this is the transport of matrix, is referred to as a CL. For this, note that C0, it gives the C00, right? And we have CIL is equal to minimum CI comma JL plus CJL plus 1, and J is a node at level L plus 1 also, right? So this is the case of shortest path problem related to the shortest path method. Then go to the next problem. This is a 0 by 1 can aspect problem. We can also use this formula related to the cost of reaching the goal node R from any node at level L is, this is a 0 less than L and less than R minus 1 is, these are the different types of formulas, and this is the general formula for nth cost associated with it. Just you see here. So we can express the solution of the problem as a modified sequence of matrix vector product, and by replacing the addition operation or by minimizing and the multiplication operation by addition, in proceeding set of equation becomes CL equal to ML L plus 1 into CL plus 1 also, where CL and CL plus 1 are n into 1 vectors representing the cost of reaching the goal node from each node at level L and L plus 1 also, right? So these are the different type of cost associated with this shortest path problem, right? And this is the matrix. This is the matrix related to ML comma L plus 1 also for the cost, different types of cost. And in this matrix, this is a matrix of order n into n matrix order, which entry I comma j stores the cost of the edge connecting node I at the level L to the node j at the level L plus 1. So the shortest path problem has been formulated as a sequence of R matrix vector product, sequence of R matrix vector products. And in the previous problem, this is the serial path, and here is 0 by 1 Knapp's problem related to the parallel path method. We are given a Knapp's of a capacity C and set of n object number. This is a 1, 2, dot, 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 comma n, and each object I has a weight of Wi, and the profit is Pj, right? Then the let V is the solution vector, and this V defined as a V1, V2, dot, 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 Vn be a solution vector in which Vi equal to 0. If object is here I, this is not in the Knapp's, and Vi equal to 1 if it is in the Knapp's, then the goal is to find a subset of the object to put into a Knapp's, so that I equal to 1, summation of I equal to 1 to n Wi Vi less than equal C, that is the object fit into a Knapp's, and I equal to 1 to n Pi Vi is maximized, that is the profit is maximized here, So these are the formulations used for Knapp's 0 by 1 Knapp's problem. So this is a method for consider the 2 to the power n possible subset, and n is the object, and choose the one set of object that fits into a Knapp's and maximizes the profit. For this maximizes the profit of this function. Here it is a formulation function is here, Fix equal to 0 minus infinity maximum Fi minus 1x comma Fi minus 1 comma x minus Wi plus Pi, and this is for x greater than equal 0 if I equal to 0, x less than 0 if I equal to 0. So for this case, I less than equal to means 1 less than equal to I and less than equal to nh here. So this is the Knapp's problem relation for this case. And Then move to the MCQ problems, and the MCQ problems is very important for any tutorial lecture or any theoretical lecture. And this is the first MCQ problem. And which of the following are the property and properties of dynamic programming problem? The four options are given here. First one is optimal substrate, overlapping subproblems, greedy approach, both optimal substrate and overlapping subproblem. So the correct answer for this question is here. D is the correct answer for this problem. So move to the next problem. So this is the second problem. If the optimal solution can be created for a problem by constructing optimal solution for its subproblems, the problem processor property, just like a overlapping subproblem, optimal substrate, and memoization and the greedy. And the correct answer for this question is here optimal substrate. Optimal substrate is the correct answer for this question. And then move to the next problem. If the problem can be broken into some problem which are reused several times, the problem processes property. These are the four options: overlapping subproblem, optimal substrate, memoization and greedy. Then the correct answer for this problem is overlapping subproblem, and the problem processes overlapping subproblem property. So this is the right answer for this question. And then move to the next question. If the problem can be solved by combining optimal solution to non-overlapping problems, the strategy is called dynamic programming, greedy, divide and conquer, and recursion. So the strategy is called the divide and conquer here, right? So move to the next problem. This is a very good question. A transportation problem is said to be unbalanced when total supply is not equal to total cost, total demand, both A and B, and none of the above. If total supply is not equal to the total demand, so this is the unbalanced problem. So B is the right answer for this question, right? And then move to the next. When dynamic programming is applied a program or problem, it takes far less time as compared to other methods that don't take advantage for overlapping subproblem. This is true or false? This is a true statement. So A answer is correct for this question. Move to the problem number 7. When dynamic programming is applied to a problem, it takes far less time as compared to the other methods that don't take advantage of overlapping subproblem. So this is a false statement. So the correct answer is here. B is the correct answer. Move to the next problem. In the dynamic programming, the technique of the storing the previously calculated values is called the saving value property, storing value property, memoization and mapping. So this property is previously calculated values is called the memoization, right? So C is the correct answer for this question. And then move to the when top-down approach of dynamic programming is applied to the problem, it usually decreases the time, complexity, and increase the space complexity. So B is the right answer for this question. And move to the last question. This is the question number. Which of the following problem is not solved by dynamic problem? So 0 by 1 can aspect problem, this is solved by the dynamic programmer. Matrix and multiplication, this is solved by the dynamic programming. Added distance problem solved, and fractional can aspect problem, this is does not solve by the dynamic programming. So D is the correct answer for this question. And then move to the references of this slide lecture. These are the different references which we will take for this lecture, and very thanks for the lecture and for your kind of attention for this lecture. Thank you again. Thank you all of you. Thank you.